All right, we have another traveling wave problem here. This is given to us as a wave on a string. It's a transverse wave, and we're given the wave function. Again, I give you the wave function in this way that they're often presented, and that is without units, just sort of in a mathematical presentation. And that's why I would like to go through and model for you putting in the units into the equation because they're rarely handed to you that way. We're told here that x and y are in centimeters and then t is in seconds. So the first thing I'm going to do is just rewrite the equation by putting the units in, and really that's to make it into more of a quantity that's easier to parse. So the amplitude, I'm told that x and y are in centimeters. So this amplitude is 15 centimeters, and you can change that to meters right now if you want to. I'm going to stick with what's given here, multiplied by sine of, now let's look at this. This is pi x over 8. All right, so pi x over 8, I'm going to change that to 8.0 centimeters, right? So the units have to cancel with the pi, I'm sorry, with the x, remember, because we need a dimensionless value in this argument for the sine function. Minus, remembering that radians are dimensionless, 4 pi, and we can change this to, let me write it this way, 4 pi radians per second multiplied by t. So we remember that that's our omega. So the general function, remember, is sine of kx minus omega t. So remembering that those quantities are in there. All right, part A here asks us to find the speed of a point on the string at a particular spot at a particular time. So really what this is about is just like using our equations here. So this is the speed of a particular spot on the string. So this is going to be, imagine your little spot in the string. What you're doing is simple harmonic motion. And if we say the string is oriented horizontally, then the simple harmonic motion would be happening vertically, right? So that's what we're focused on describing here, the speed of any point on the string. This is different from the wave speed. They're not asking us for the wave speed. They're asking us for the speed of a point on the string, and that particle, that point on the string, is undergoing simple harmonic motion, right? So one of the things you expect right away is that the function for that speed is going to be a sinusoidal function. Because as you know, in simple harmonic motion, that speed isn't constant, right? It's constantly changing, in fact. So let's first just look at the function here. So the velocity is going to be a function of x and t, and that is just the first derivative of the position function. And again, that's because we're not going after the wave speed here. We're actually trying to find the speed of a particle in the medium. So we do want to focus on this function. What that will give us here is negative 4 pi radians per second times 15 centimeters times the cosine of pi x over 8 centimeters minus 4 pi radians per second times t. Okay, so that's my function for speed of a particle on the string. And all I have to do then for that function, they're asking me for the speed at a particular place at a particular time. So they're asking me for the speed of 6 at x equals 6 centimeters, right? At t equals 0.25 seconds. And what's more is they're just asking for the speed, not the velocity. Notice that this function will give me a signed quantity. So I'm going to want the absolute value of that. So if I plug in those values and do that particular calculation, I should get something that's around 1.33 meters per second. And we would expect one particular value there because it's asking us for the speed of a particular point on the string at a particular time. if they just asked us like, what's the speed at x equals 6? Well, that would still have to be a function, right? Because that is gonna change over time. That particle is in simple harmonic motion. But because they're asking us for a particular point on the string at a particular time, what I expect there is at one value. It will have only one speed at that point. Okay, moving on. So part B, the maximum speed of any point on the string. Okay, so this is kind of cool. Look at the equation that we expressed here for the speed of the string, the velocity equation there, right? So this actually velocity of a point on the string. I can put hats on these guys because they are signed and those signs are meaningful. Now so if I look at this equation here and I ask you, what is the maximum value of that? Right? What is the maximum value of that? Well, the good news is here, this is a sinusoidal function, isn't it? So what we know is that the maximum value of the cosine part is equal to what? 1, right? That's true for whether it's cosine or sine. So the maximum value of the whole cosine part is equal to 1. What that means is that the maximum value of the entire function is just what's sitting in front of the function, so the coefficient that's sitting in front of it. So that tells me that V max, and again, we're wanting maximum speed, so I can just do absolute value, is going to just be equal to 4 pi radians per second multiplied by 15 centimeters. So that'll give me 60 pi centimeters per second, which is about 1.88 meters per second. If you just want to wrap your head around how fast is that. So finding maxima is really convenient when you have these cosine and sine functions, right? Because they max at 1. So it really makes things simple, which is nice. So part C asks for us for the magnitude of the acceleration at any point on the string. So for that part, we would do like we did with the velocity, right? We know that acceleration is equal to dv dt here, and we can solve for that function. And then once we have that function, substitute in for the particular point that they're asking us for. So again, they're asking us for 6 centimeters and 0.25 seconds. So you would go through the exact same process as A. So same process as part A. And then to find your value there, the result here should be that the acceleration at 6 centimeters and 0.25 seconds is equal to the absolute value of that is equal to 16.7 meters per second squared, because they're just asking us the magnitude of acceleration there at that particular moment in that particular spot. And then, of course, part D asks us for the magnitude of the maximum acceleration, which you're probably wrapping your head around right now. So once you have, again, that would be the same as part B. Once you have expressed your acceleration, it'll be in terms of a sine function, but same thing, sine function maxes at 1, right? So you're really just focused on that coefficient that's in front of that sine function. And as usual, all the details can be found in the written solutions.